Hi, let's talk about synchronous rectification. So why we talk about this technique? Well, we have been working with this buck converter design, and when we identified the different types of power losses, we realized that the diode conduction was the main contribution to the total power losses. So with this technique, we will be able to reduce this problem. So what is the idea of this technique? It's very simple. What we are going to do is to replace the diode with a MOSFET. And when we do this, or when we apply this technique, we apply this synchronous rectification when the diode conduction is the main contribution of the total power losses, as in our case, and moreover, when the MOSFET we use for replacing the diode has a own resistance that is better in terms of power losses. I will explain that with more detail. So we know that when the diode is in non-state, we model that operation as a voltage source whose value is VF, the forward voltage drop, and well, in the case of the Schottky diode was 0.5 volts. When we use a MOSFET, what we know is that we have the own resistance, and basically the idea is that the power consumed in this resistor must be lower than the power consumed in the constant voltage source of the diode. So basically that is the idea. An important point that we must take into account is that the current that is driving this MOSFET is a little bit special, because if you remember the main MOSFET of our buck converter, this one, when we evaluate the current through the MOSFET, we draw the current in this way. So the current flows from the drain to the source. But in this new MOSFET, the current flows from the source to the drain. So we call this situation or this operation third quadrant operation. Okay? And it means basically that the current flows from the source to the drain. Well, so basically the idea is that we are going to implement this topology, which basically is the synchronous buck converter. When we replace the diode with a MOSFET, we talk about synchronous rectification buck converter. And a very important point we have to take into account is the dead times. We introduce dead times, or we include dead times in the control signals of both MOSFETs in order to avoid the situation or a situation in which both devices are in on state at the same time. If both devices are on at the same time, we have something like this. Here we have a short circuit, here we have a short circuit. So the problem is that we have a high current flowing in this way, and probably that current will destroy the buck converter. So in order to avoid that situation, and taking into account that the switching process of a MOSFET requires some time, we need to wait some time between the turn off of a MOSFET and the turn on of the other MOSFET. So that amount of time is the dead time. Let's see the control signals for this buck converter, and as a consequence where we have the dead times. So the first waveform is the classical waveform that we have seen in previous videos, is the control signal of MOSFET SA, the main MOSFET. So it's the same as in the previous cases. We have a pulse width of D times the switching period. In the second case, what we see is the control signal of the second MOSFET. Ideally, when we turn off the main MOSFET here, we turn on the second MOSFET here. And when we turn on the main MOSFET here, we turn off the second MOSFET here. But as I said, we need some time to complete the switching process of our MOSFET. So as a result, in order to avoid the situation in which both devices are on at the same time, we have this gap here. So this part, this time interval, is called the dead time. And here we have another one. So essentially we include those gaps in order to avoid a short circuit with the input. Okay. Well, so let's see. Once we know that we have these control signals, let's see the path followed by the current of the inductor in each stage of this switching period. So, for instance, in this first interval, I think that it's very easy to realize that MOSFET SA is on, MOSFET SV is off. So the only possible solution is that the current flows through the main switch, through the main MOSFET, like this. The question is, what happens in this scenario during the dead time? Assuming that the turn-off process of the main switch has finished, so it's off, and we are still in a situation in which the second MOSFET is still off. So both devices are off. What is the path for the inductor current? This one or this one? So in order to answer that question, we must take into account that every MOSFET includes a body diode. This is like a parasitic diode that is connected in this way, okay? All MOSFETs include this body diode. And once we consider these parasitic elements, we know the answer of this question. So during this interval, the inductor current must flow through the body diode of SV. Okay? Well, after that, since we want to minimize conduction losses, we activate the second MOSFET in this part. What is the current path in this situation? Well, in this situation, the current is going to flow through the MOSFET channel, okay? Because, well, we assume that the on resistance, the RDS on, is small enough. Well, and then we have another dead time. What is the current path for the inductor current? Well, this MOSFET is off, this MOSFET is off, we have current flowing this direction, okay? The answer is that it will activate the body diode of MOSFET is SV. So in summary, during the dead times, the body diode of MOSFET SV is activated. So before we finish, let's evaluate or let's talk about what is the impact on the losses of SV. Okay, we are going to analyze the power losses in this switch, considering both the MOSFET itself and the body diode. So, well, it's clear that we will have conduction losses, mainly during the MOSFET activation, okay, when the current flows in this way through the MOSFET. Okay, but it's true that during dead times the current will flow through the body diode. However, we are going to neglect this kind of power losses because we are going to minimize the dead time. So in this way, we are going to consider that this part is negligible in terms of power losses. Okay, what about the switching losses? Well, one part will be the turn-on process of the MOSFET. So before we turn on the MOSFET SV, the current was flowing through the body diode, and in that situation, the voltage across that body diode was more or less zero. So when we turn on the MOSFET, the voltage across it was already zero. So we don't have voltage and current at the same time. So we will consider that during the MOSFET turn on, in the case of SV, power losses are negligible. Well, what about the MOSFET turn off? Okay, the MOSFET turn off, or in order to analyze this situation, we have to point out that, well, the current was flowing through the MOSFET channel, and after we turn off the MOSFET, the current will activate the body diode. So, in this situation, the voltage before the change is 0 volts, and the voltage after the current change is more or less 0 volts. So, as in the previous case, the power losses about this process can be considered 0. Okay, so with this we finish with the MOSFET SV. Let's talk about the body diode. What happens with the switching losses in that body diode? What happens when we turn on or the body diode turns on? So the answer or the assumption that we are going to consider is that it's negligible. Why? Because as in any diode, the turn on process is very fast. So, as we always do, we assume that it's 0. What happens when we turn off the body diode? So in that case, we know that we have to consider the reverse recovery of the body diode. And the turn off of the body diode appears 2 times per switching period, in both at the end of each dead time. So at the end of the first one, the current was flowing in this way, and after the dead time, the current flows in this way. So in this situation, the reverse recovery is negligible because there is no voltage change. What about the second turn off of that diode? The second turn off of the diode, of the body diode, takes place at the end of the switching period. Okay, is at the end of the second dead time, and in that situation the current was flowing through the body diode, and after the change the current flows through the channel of the main switch. In this case the situation is different. It's the conventional situation that we have studied in previous videos. So in this case we have to consider the reverse recovery, and the conclusion is the same of the previous explanations. The reverse recovery is a process that mainly affects the opposite MOSFET. Okay, so we know that we will have a reverse recovery current, but it will be driven by the main MOSFET, and that MOSFET is going to have higher turn-on losses. So in this case, in the body diode, the power losses are negligible, but we have, or we must take into account that this reverse recovery process has a high impact on the main MOSFET, and in particular during the turn on of that MOSFET. Okay, well, so with this we finish with the main part of this video, but I want to include a final comment taking into account this last point, the reverse recovery of the body diode. And that final comment is that a typical approach to alleviate the last problem, the reverse recovery impact on the main switch, is to include a Schottky diode in parallel with MOSFET SV, something like this. This one is a Schottky diode. Why we do this? Because in general the body diode of a MOSFET is a very bad diode in terms of conduction losses, and especially in terms of reverse recovery. So in order to minimize the impact of that body diode on the main switch, we include the Schottky diode, because we know that the reverse recovery or that Schottky diode is very good in terms of reverse recovery. And basically with that Schottky diode, what we do is that instead of activating the body diode, we activate the Schottky diode. And in this way, the turn-on process of MOSFET SA involves Schottky diode, not the body diode of MOSFET SV. Well, so with this we finish. In the future videos we are going to see the results of simulating a synchronous buck converter, And we are going to evaluate or validate the ideas that we have seen in this slide. So thank you and see you